this section of the notes is called important terms for inference, and I'm not going to spend a lot of time with this because these are things that are covered in previous videos. So let me just do a quick read through of this, and then we'll go on to our next topic. The null hypothesis is what you believe unless the data convinces you otherwise. It's the status quo. It's the original claim. It means the original assumptions have not changed. Basically, it's boring nothingness. Nothing's happening. Nothing's changed. The alternative hypothesis is the exciting thing. That's what you're trying to find evidence for. If we have a one-sided test, we're looking for evidence that the population parameter is either greater than or less than the null hypothesis value. If we have a two-sided test, we're looking for evidence that the population parameter is just different from the null hypothesis value. Remember that these hypotheses are set prior to collecting the data. So you don't wait until you see your sample statistic and then decide what your alternative is. You set your alternative based on the question you want to answer. Okay, two possible explanations for an observed sample statistic that is unusually far from the null hypothesis. So let's say you get a p-value of like 0.02 or something. The null hypothesis is still true and we got an unusual sample just by random chance, or the unusual sample is evidence that the null hypothesis is false. Now the thing is, we don't know which of these is correct when we do a hypothesis test. So there is always a chance that we have made a mistake, and that's what we're going to talk about today, is what are these mistakes that we can make in hypothesis tests. The p-value is the probability that you would obtain data at least as extreme as those obtained if the null hypothesis were not true. And this would be in the direction of your alternate. So if you are looking for something less than, it would be at least that much less than or more extreme. If you are looking at a two-sided hypothesis, then it could be that much extreme, that much greater or less than the null hypothesis. You put the two together. The smaller the p-value, the more likely we are to reject the null hypothesis. Now this leads to the question is, how small is small enough? So this is the definition of a significance level. A significance level sets a threshold for our p-value. If the p-value is less than that significance level, we reject the null hypothesis and say there's convincing evidence for the alternative hypothesis. If the p-value is greater than that threshold value, that alpha, we fail to reject the null hypothesis and say there is not convincing evidence for the alternative hypothesis. Notice we never say that the null is true. Okay? Our choice for alpha depends on the situation. How strong does the evidence need to be? If no significance level is specified in the problem, it is common to use a 5% significance level. So let's say, I want to have some kind of an example here, so I'm going to use one from the book. In the perfect potato examples in the book, which is on page 549, we have a situation where we're saying that the proportion of all potatoes with blemishes in a shipment of potatoes to a potato chip factory has to meet a certain standard in order for them to accept the shipment and go ahead and use those potatoes. The standard that is set is our null hypothesis. The null hypothesis says that p is 0.08. In other words, 8% of the potatoes have blemishes. The alternate hypothesis is that p is greater than 0.08. If it's greater than 0.08, we'll reject, if greater than 8% of the potatoes have blemishes, we'll reject the null hypothesis and not accept the shipment. Okay? So we're saying 8% or less is okay, but if it's greater than 8%, then we're going to reject the shipment of potatoes. This is known as the p null value. In other words, this is our null hypothesis value for p. So that's symbolized p naught. So in here, so we're going to say this curve here represents the distribution of sample statistics we could get from the population with 8% defects. So here we're going to just say this is 0.08. Now, if we were to run a hypothesis test and we were to get 9%, okay, so, or let's just say 10%. Okay, so let's just say that we got a p hat is equal to 0.10. We got 10% defects. Actually, that's going to be more over here. Okay, p hat equals 10%. And you can't really see that very well. Let me do this in black. P hat equals 0.10. okay, if we got p hat equals 10%, then this is going to cause us, if this is, let's say this is far enough away that this is going to cause us to reject the null hypothesis. All right. Now I don't know for sure what the standard deviation is. Actually, I could figure this out. Probably should have done that. Let's see here. Yeah, p hat of 10% does cause us to reject the null hypothesis. I had to look at the example in the book. So if this would be far enough away, enough standard deviations away from 0.08 to cause us to reject the null hypothesis. So if we reject the null hypothesis and there really are only 8% defects, then we've made a mistake. If we reject the null hypothesis and there really are more than 8%, then we've done a good thing. So let's let this curve represent the true proportion of potatoes with blemishes in this shipment. So let's say the true proportion of potatoes with blemishes in this shipment is 11%. So let's say this is a bad shipment of potatoes. So if this were true, if the null hypothesis is not true and there's really 11% bad potatoes and I get a sample proportion of 10% and I reject the null hypothesis and I say, take those potatoes back, we're not making our potato chips with those, I've made a really good decision. So if we reject the null hypothesis when the null hypothesis is false, that is a good decision. Okay, so that was when my p hat equals 0.11. Okay, if the null hypothesis is really false, I made a good decision. But what if the null hypothesis is actually true? Could I have gotten 10% blemishes in a random sample from this population? Yeah, I could have. I wouldn't get it very often, but I could have gotten that. So if I reject the null hypothesis when it's really true, I've made what's called a type 1 error. Now, how often am I going to make a type 1 error? Well, I'm going to reject the null hypothesis when my p-value is less than alpha. So if there's only a, if my alpha is 5%, if there is only, if the p-value associated with this sample proportion is like 4%, I'm going to reject the null hypothesis. But guess what? 5% of my samples from this population are going to be in what's called the rejection region, because I'm looking for any p-value less than 5%, so there are going to be 5% of the time that I could get a sample proportion from this population that would cause me to reject the null hypothesis, even if it's true. So the probability of a type 1 error is just my significance level. The probability of a type 1 error is alpha because that's the percentage I set for my threshold for my p-value. So if I want to be very certain that I don't make a type 1 error, I'm going to make my alpha level smaller. If I want to be very, very convinced and not certain, and be certain not to make a type 1 error. Now we also have a type 2 error. So I'm going to say this probability of a type 1 error here is alpha. Now, we could also make a type 2 error. Now, a type 2 error occurs when maybe I get a p hat over here. So let's say I get a p hat of 0.9, or 0.09, I should say. And this p hat of 0.09 is close enough to the 0.8 that I don't reject the null hypothesis. And if the null hypothesis is true, failing to reject it is a good decision. Oops, get that out of the way. That would be a good decision. But I could have also gotten a p hat of 0.09 from this distribution where the true population proportion is really 11%. In that case, I would have made a mistake. I would have said, hey, you know, this is actually coming from a sample. I've really got a sample with 9% blemishes in this shipload or this truckload of potatoes where it was really 11% blemishes, and I failed to reject the null hypothesis. So I made what's called a type 2 error. The type 2 error, and I'm going to write it with a 2, type 2 error. The type 2 error is failing to reject the null hypothesis when it's false. and the probability of a type 2 error is called beta. Now, beta is a number that you are not ever required to calculate in the AP Statistics program here, but it is just the, so you just need to know it's beta, but you don't have to know how to calculate that. If you get any questions about a type 2 error, you'll just be given that value, or it'll just be more general questions. But you do need to know that alpha, the significance level, is the probability of a type 1 error. We'll be talking more about type 1 and 2 errors in the next two sections, so if this is a little fuzzy for you right now with these graphs, that will become more clear. But on the next page of the notes, we're going to look at some examples of what's a type 1 and type 2 error and what are the consequences of that. So let's turn to the next page in the notes. And I'm going to actually cover this up so we can kind of look at them one at a time. So first of all, remember that a type 1 error is rejecting the null hypothesis when it is really true. Kind of get this up here. Rejecting the null hypothesis when it's true. Type 2 is failing to reject the null hypothesis when it's false. There probably shouldn't be a little dash in there. So let's think about a criminal trial. Is the defendant guilty of the crime? So let's think of our two hypotheses. The person is innocent is the null hypothesis. So we're always, innocent until proven guilty. The person that the person is guilty is what we're trying to find evidence to prove. If you are, if this person's on trial, they're trying to find evidence to prove they're guilty. Notice we can't find evidence of innocence. You can only find evidence of guilt. You're just assumed innocent unless we get enough evidence to prove you're guilty. So that's important to remember. So what's a type 1 error in this context, and what are the consequences? Well, rejecting the null hypothesis when it's true. So rejecting their innocence, saying they're guilty when they're really innocent. Saying guilty when the person's really innocent. So what's the consequences of that? Well, there's an injustice. You're punishing an innocent person. What would be a type 2 error in this situation? Well, you would say the person is guilty, but the evidence says not guilty. Or the person is really guilty, but the evidence says not guilty. There's not enough evidence to prove they're guilty. So what's the consequence of this? A criminal goes free, maybe commits more crimes. Sometimes we say, which of these is a worse situation? Well, it kind of depends on your point of view for some things, but in our country, we usually say that a type 1 error in this case is worse, because we would prefer to occasionally let a guilty person go free rather than to condemn an innocent person. That is the basis of our justice system. So there is more burden of proof put on proving guilt than on proving innocence. An innocent person doesn't have to prove they're innocent, but somebody that is accusing them of something has to prove their accusation. Okay, so let's look at the next example. In a clinical trial of a new drug, is the new drug effective in treating the disease? So the null hypothesis would be the drug isn't effective. It doesn't make any difference. It doesn't matter. I'm not sure why I wrote doesn't matter, to be honest here. That's kind of a silly thing to write. It doesn't work. Doesn't work. Okay, it doesn't make any difference. It doesn't work. Here the drug is effective. So that would be what we're trying to find evidence for, is that the drug is effective. So what would be a type 1 error? Type 1 error, remember, is rejecting the null hypothesis when it's true. So we're saying, we say the drug works when it really doesn't. We say the drug is effective. We've rejected the null hypothesis, meaning saying we think the alternate is true. But it's really not, it really doesn't work. The consequence? People use a drug that doesn't work. A drug company sells a drug that doesn't work and gets sued. People using a drug that doesn't work, they don't get cured, maybe they die. Okay, so there's a lot of consequences to this. A type 2 error in this case would be saying that the drug doesn't work when it really does. There's not enough evidence to reject the null hypothesis even though it's false. Even though the drug really is effective, we don't find enough evidence of that. The consequence, patients miss out on an effective treatment and a company doesn't make money on the drug. Okay, last example here. Quality control. Do the parts meet the required standard? Okay, so we're going to say for the null hypothesis here is that they meet the standard. And because what we're looking for is examples that they don't. Like we're looking for flaws in the parts. When we're doing quality control, we're not going, oh, this is a lot of good parts. We're saying, is there anything wrong with them? We're looking for things wrong. That's what we're looking for evidence of. So for example, let's say our standard is that only 2% of the parts or less are defective. And if that's the case, we're going to say the parts meet the standard. But if more than 2% of the parts are defective, then we'll say the parts don't meet the standard. So you're going to do something like that with percentages or means or something to define this. So type 1 error in this case would be that saying the parts don't meet the standard when they actually do. Reject the null hypothesis when it's really true. The consequence, of course, would be the company can't sell their good parts that they have, and they lose some money. Customers can't get the parts they need. The second one, what's a type 2 error in this case? We're saying that the parts meet the standard when they actually don't. Now realize, of course, we can't prove they meet the standard, but we don't have enough evidence to say they don't. So the company continues to sell their defective parts, has unhappy customers, maybe they even get sued, maybe the defective parts could be dangerous. So this is what is meant when we're saying interpret, define and interpret a type 1 or 2 error in the context of a problem, and then give its consequence, give a possible consequence.